I'm calling this problem multi-step integration. It's going to give us an opportunity to work through a review of polynomial long division. We're going to use some partial fraction decomposition. We're going to need to use trig substitution as well. And what I'd like, to suggest that you do if you're watching this video is attempt the problem on your own for some amount of time, then go ahead and watch a section of the video to see if the work that you've done matches up with the work that needs to be done in order to come out with the correct answer. And then backtrack if you need to through your version of the work to make any corrections, get caught up to speed, and then work ahead again on your own through the next step or set of steps to see if you can make progress again on the problem, and maybe do that 3 separate times, one for each part of the problem as we're going to do it with long division, partial fractions, and trig substitution, and then maybe some final integration steps. You might do that separately too, but that's up to you. All right, so let's get started on this because I think it's going to take a while for me to even get through an answer. So the first thing we need to notice in this integral, obviously it's complex. We know that we're going to need to use some of our complex integration techniques that have already been mentioned. We also need to know, though, that the degree in the numerator of this integrand is greater than the degree in the denominator, which means before we want to do anything with partial fraction decomposition, we want to do long division to break off some pieces to the front of the fraction. So let's go ahead and do that. We're going to set up our long division bar here. We've got our numerator inside, x to the 4th plus x cubed plus 10x squared plus 12x plus 12. And we need to expand, obviously, the denominator for the division that we're going to do. And so we've got x cubed plus x squared plus 9x plus 9. I got kind of squeezed there, but should work. We'll keep going. And we're going to ask, as we do this long division, remember, what would I multiply x cubed by to get x to the 4th, and we'll let the rest of things fall as they may. The answer, obviously, is x. We're going to put that in a column here for x values, and then we're going to perform the multiplication. When we do that, we get x to the 4th plus x cubed plus 9x squared plus 9x. And I like to put those in parentheses and a negative sign in front just to remind me what I'm doing so I don't lose track of the subtraction that's going on. And then I'm going to get x squared here. 10x squared minus 9x squared is x squared. And 12x minus 9x is plus 3x plus 12. Bring down the 12. And I'm already done with the polynomial long division now. I was able to get this x. That's how much this goes completely into the numerator. And now what I have left, x squared plus 3x plus 12, x cubed polynomials, right, with a degree 3 can't go into that at all. So this is my remainder, and I'm going to go ahead and rewrite up here my new integral. Right, the fraction that I started with is now a new combination of x and a new fraction, x squared plus 3x plus 12 divided by x plus 1 times x squared plus 9. now I have a fraction in my integrand that is appropriate for partial fraction decomposition. It has two factors in a completely factored denominator, one linear factor x plus 1, one quadratic factor x squared plus 9. So to set up my partial fraction decomposition, I'm going to rewrite the integral as x plus some constant a over x plus 1 plus bx plus c over x squared plus 9. Remember that when we have a linear factor in the denominator, it gets a constant numerator. When we have a quadratic factor in the denominator, it gets a linear numerator. All right, and we're going to be basically focused on making these equal. So I'm going to leave the integral and the x term alone for a while and just focus on what I just put that box around. So those have a common denominator. I'm going to multiply both sides of an equation. Maybe I'll just go ahead and write it out. I think I've got enough space, and that'll be helpful, I think, if we're lost at all. X squared plus 3x plus 12 over x plus 1, x squared plus 9 needs to be equal to a over x plus 1 plus bx plus c over x squared plus 9. So now it's easier to see where we're talking about having a common denominator. This is the common denominator for both sides of the equation. We're going to multiply both sides by that, and it will cancel on the left. We're just going to have x squared plus 3x plus 12, and on the right, the x plus 1 cancels in the first fraction, and we have a times x squared plus 9. The x squared plus 9 cancels in the second fraction, and we have bx plus c times x plus 1. Now we're at the step where we need to do some expansion and then grouping of like terms. So we've got ax squared plus 9a plus bx squared plus bx plus cx plus c. And I said I was going to group them, but it's easy for us to see where the x squared terms, x terms, and constant terms are in that list. So now we're going to just go ahead and set up our system. Right, we know that the coefficients of x squared on both sides of the equal sign need to be the same. So in other words, we know that a plus b needs to be equal to 1. We know the coefficients of the x terms need to be the same. That means b plus c needs to be equal to 3. And lastly, the constants on both sides of this equal sign need to be equal, and that means 9a plus c is equal to 12. So a quick canceling of or eliminating of c's would be a good place to start. If we take the opposite of the second equation and combine it with the third equation, then we're going to get 9a minus b is equal to 9. And we can put that together with the first equation, a plus b equals 1. That'll eliminate b's, and we have 10a equals 10. So a is equal to 1. Going back to right here, if a is equal to 1, then b is equal to 0. If b is equal to 0, then c is equal to 3. So now I think I'm ready to go all the way back to my full integral and continue on with this process. So I'm going to write it over here. Now I know that this integral is equal to the integral of x plus 1 over x plus 1 plus 3 over x squared plus 9. And I'm starting to see some opportunities to evaluate pieces of this integral. Oh, get the dx on there. So I can take the integral of the first term by distributing my integral through the 3 terms that I have now, and I'm going to get x squared over 2, the integral of the second term, by a very simple u substitution lets me know that I have the natural log of the absolute value of x plus 1. And this last integral I'm not quite ready to evaluate. I'm going to leave it. Integral of 3 over x squared plus 9 dx. Here's the step where we're going to do trig substitution, and I've only got a few minutes left in this video, so I'm going to have to hurry up. Our denominator, x squared plus 9, right? Since we have a plus, that means we're going to do a tangent substitution. So our substitution needs to be x is equal to 3 tangent theta. Dx then is equal to 3 secant squared theta d theta. So I'm going to rewrite that last integral over here. The integral of 3 times 3 secant squared theta d theta over 9 tangent squared theta plus 9. And we simplify a lot. We've got 9 on the top and the bottom that will cancel. Then let's go ahead and write that step. We have secant squared theta d theta over tangent squared theta plus 1. So the denominator is also secant squared theta. Those will cancel, and we have the integral of d theta is equal to theta plus c. Resubstituting for theta, we have arctangent or inverse tangent of x over 3 plus c. And that means we're ready to write our completed answer. So all the way down from the top, we have x squared over 2. That's the part of this we were able to determine simply by polynomial long division, plus the natural log of the absolute value of x plus 1. Our partial fraction decomposition and u substitution allowed us to get that part. And then finally, trig substitution gave us the integral in our last term. We have inverse tangent of x over 3, and don't forget the constant of integration. So there's our answer. Hope that was helpful. May need to watch it again to get everything out of it, but I think we're good to go. Thanks for watching.